Hi, this is Nazanin, and I'm gonna to talk about weakly supervised deep instance nuclei detection using point annotation in 3D cardiovascular immunofluorescent images. Atherosclerotic disease is a life-threatening disease. This condition is a process in which deposits of fatty materials called nuclei builds up inside the walls of arteries, reducing or blocking blood flow. In extreme cases, it may lead to heart attack or a stroke. Based on the clinical studies, the composition of the plaque is indicative of adverse clinical events. The plaque composition can be determined by cell count statistics within atherosclerotic plaque lesion. This is an example of immunofluorescent image of the lesion. It contains 5 different color channels, and the blue color indicates the nuclei in these images. Our goal here is to detect and localize nuclei in these images. These images have variety sizes in the dimension, and here we see layer 10 out of 10 layers. This is the diagram of our proposed approach. Here, to train the model, we need fully annotated segmentation masks, but this process is expensive. So we ask experts to perform point annotations, and since these images have variety sizes in the dimension, we collapse these three-dimensional images into two-dimensional images by using maximum intensity projection. Also, since we cannot use point annotation to train the model directly, we generate pixel-level labels by following Q's approach. In this approach, we apply k-mean clustering over the RGB values. And then we assign label nuclei to the cluster with maximum overlap with the point annotation, which is shown by green. And we assign label background to the cluster with minimum overlap with the point annotation, which is shown by red. And finally, we consider the remaining cluster as an ignored area, which is shown by black. In this paper, the authors suggest to not train the model over the ignored area. However, this area may contain important information. In this paper, we propose to train the model over the ignored area. We adopt semi-supervised learning approach, and we use entrée minimization loss to train the model over the ignored area. We adopt HoverNet architectural model, and we extend this model by adding entrée minimization loss. These are the results. First, we train the HoverNet model with weakly supervised learning setup, and then we compare its performance with other baseline methods. The HoverNet model outperforms other baseline methods. Then we extend the HoverNet model and Q's model by adding entrée minimization loss, and we achieve better results. These are our contributions. First, we demonstrate that the HoverNet model requires no modification for training in weakly supervised learning setup. Second, we adopt a semi-supervised learning approach to train the model over the boundaries of the nuclei. Third, we adopt the HoverNet model to detect nuclei on the three-dimensional immunofluorescent images using point annotation. And finally, we show that the HoverNet model has better generalization capability in comparison with the current weakly supervised learning approaches. Thank you for your attention.